Well, this is John Black, Super Chemist. I hope you remember that on the left side of the periodical table is the metals, and on the right is the non-metals. Okay, these are the noble metals, or the noble elements. Remember, they have their octet. That's what makes them great. That's why they're at the end of the thing. Each time you add an electron, it'd be 1, 2, 3, 4, 5, 6, 7, 8. So you got 8 electrons in your valence shell. Now remember, the lefts, why do they, on our list, if you remember your list, you got a negative side and you got a positive side. Why is the metals on the negative side? They're on the left, so obviously they're negative. When I say that they're negative, I mean that they act like they're negative. Remember, these they only have 1 or 2 electrons in their valence shell, so they want to get rid of them to have an empty shell, so the shell before it becomes full. That's why I say they're negative. They're not really negative. Metals are not negative. They're neutral. But they want to get rid of an electron if they can. Okay, just like over here, say oxygen. Oxygen only needs 2 more electrons to fill up their valence electron and be noble, like a king. These are the kings over here. So they're going to accept, even though they're, an O is not positive or negative, it's neutral. But it wants negative things. You know what I mean? If I come to you and I take a negative thing away from you, like a bill, that makes me a positive person, right? Same with oxygen. But think about a metal. A metal is on the left side of the periodical table. It's negative. Another way, where do metals come from? Metals come from dirt, okay? Metal people are dirt, right? Remember, think of these as kind of like people. Metal people are dirt people. They're nothing. They're always trying to, give you something like a bill, mooch off of you. And think about a non-metal. Non-metal, like oxygen, chlorine, all the non-metals, a lot of them are gases, you know what I mean? They're free. They're close to the noble elements. They're like nobility almost. They're good heavenly people, you know what I mean? And in our instance, they have protons to give us. Protons are positive. So anyways, I want you to look at these 2 lists and see what's, the main things are negative and positive. But we're going over acids, right? So once you look on a thing, I'm going to show you here's an acid, here's a proton. A proton is positive. Acids are positive. Look over here. The opposite would be base. Bases are negative. OHs are negative. I want you to see how a proton and an OH, that adds up to water, doesn't it? Positive and negative is a neutral water. So anyways, the first acid we're going to go over is an Arrhenius acid. And basically it's just a substance that increases the concentration of protons when added to water. Okay, if you add it to water and you got more protons than what you started with, then it's an Arrhenius acid. An Arrhenius base is the other side of the water molecule. This is the proton. This is the hydroxide ion, the OH. It's negative. So an Arrhenius base is a substance that increases the concentration of hydroxide ions when added to water. You can see there's the proton, there's the hydroxide. That's a water molecule. I want you to keep in mind, though, when you have an acid like this, the protonation is, first of all, instant. You know what I mean? That's the first thing that happens in any reaction. If there's any protons, they're going to be jumping around. And if you put them in water, you're going to make hydronium ions, okay? Like when you have HCl in water, it's making a hydronium ion. And here it is right here. It's adding on an H. The proton jumps onto the water molecule, makes hydronium. That's your actual acid. You know what I mean? In most reactions, that's what happens. And then it jumps from this hydronium ion to the base in the reaction. Now this is the type of acid that pH was made for. Okay, the other two acids doesn't necessarily have pH. Okay, so the pH, what does it stand for? Well, the H stands for the concentration of hydronium ions or protons that are floating around in solution, right? The P is the negative inverse log of, and it's right before the H, so it's the negative inverse log of the concentration of hydronium ions or protons in the solution. So let me just give you an example here. Let's say your concentration is 10 to the negative third power. That means your pH is 3. All I did was remove the 10 and change the sign on the 3. Let's say you have a concentration of hydronium ions and it's 10 to the negative 2. Well, the pH is 2. That's why when you get more hydronium ions, it's more acidic, right? That's why it fools you with the pH, because the pH isn't telling you the concentration of the protons or hydronium ions. It's giving you the negative inverse log. So every time, so see how this 10 to the negative 2 is actually a bigger number than 10 to the negative 3, but the pH went down. It went up here, but it went down here on the pH. Concentration went up, pH went down. To let you know, pH above 7 is alkaline, pH below 7 is acidic. As we just said that, more concentration, less pH. So it's more acidic. Above 7 is alkaline, 7 is neutral. You might ask, well, why is water a 7 if it's neutral? Why is 7 neutral? If 7 tells you that there's a concentration of hydronium ions in there, then it must be acidic. But look at this equation here. Water actually self-ionizes in a disproportionately way. You can see you got two water molecules. One gets oxidized and one gets reduced. One to hydronium and one to hydroxide. Now the thing is you can see each time you get a hydronium ion, you also get a hydroxide ion. So even though you do have, because if it's a pH of 7, that means your concentration of protons is 10 to the negative 7. But your concentration of hydroxides is also 10 to the negative 7. If it's the same as this, right? If these are equal in concentration. So that basically makes it neutral because they're canceling each other out. You know what I mean? But they are there at 10 to the negative 7 in concentration. It's just they're equally there. So it kind of cancels each other out. Alright, here's a couple examples. Now I got the red part of each compound in red. The red is because that is actually the acid part of the molecule. And the negative blue is the base part of the molecule. But you can see I have hydrochloric acid and water. Water is going to be the base, okay? You end up with a hydronium ion, because remember, when you do that, the H jumps off onto this, right? So this jumps onto here, makes the hydronium ion, right, onto the whole water molecule, and you're left with a negative Cl. That is considered, when you go over to this side, whatever got the hydrogen is considered the conjugate acid, and whatever got rid of the hydrogen is considered the conjugate base. It's just the opposite. See how the line goes to here? Base, acid. See how this one goes to here, acid, base. But I want you to notice, see this chloride? That's a base, right? Because it's negative. It's a weak base. How do I know it's a weak base? Because it comes from a strong acid. So I know that it's the opposite. Just like this. Water is a weak base. I mean, I could drink water. So that means that the conjugate acid is going to be strong, the opposite. Okay? That's a good way to learn what's strong and what's not on acids and bases. You automatically know this is weak because it comes from a strong acid. Okay, let's look at the hydrochloric acid when you react it with sodium hydroxide. But keep in mind this is in water, and you'd actually have hydronium ions contributing to this protonation. But let's just take out the water and check it out. You got an HCl here, you got an OH, and you got a sodium here. You pour the HCl in. This is your base, right? So it needs to get a proton. This is your acid. It needs to give it a proton, right? And what does it get left with? Because this is a base, so it must be screwing this guy over, right? It's a negative whatever, right? It's a base. So what's left over is a negative chloride. You have a neutral HCl here, but it's actually, you're left with a negative Cl. So hydroxide screwed it, so it must be the base, right? This is giving, the hydrogen chloride is giving a positive proton. It's making a negative OH into a neutral H2O. I'd rather be neutral than, I'd rather have nothing in my bank account than O out money, right? So obviously, this is the acid. And that's why you say this is the oxidizer. It oxidized the OH because it took it from a negative to a neutral, which is better. Just like this reduced this. How did it reduce it? It was neutral. Now it's negative. That isn't a reduction. I don't know what is. And keep in mind, this would, like I said, this would be jumping around with the water that it was already in. HCl is always aqueous. So I'd probably start out with an H3O. But like I said, the protons are jumping around everywhere. They eventually jump back to the HCl2. So you don't know where they're coming from because they're coming from everywhere. But you see how the acid helped out the base by making it neutral, and the base screwed this guy over and made him negative when he was neutral. And that's why I always say when you get it, and this is the type of acid I'm talking about, because there's 3 types of acids. But this one is the one where I say an acid and a base makes salt water. Because if you have an acid and a base, you're going to make salt water. See? Salt water. You're always going to have water because there's an OH and an H. That's the definition of the base having an OH, and the definition of the acid is having an H. So you're going to definitely have water. And whatever's left over will be the metal here and the non-metal there, which is a salt. In any reaction, you want to know where the protons are for acids, and you also want to know where the lone pair electrons are. See how there's a lone pair electrons on these? Oxygen has lone pair electrons, so they're into a lot of reactions. Because remember, there cannot be a chemical reaction without electron transfer. So you have to have electrons to have a reaction. Otherwise, there is no reaction. So that's the first thing you want to know is where are the electrons? Because they're going to be doing something to make the reaction go. Otherwise, there is no reaction. And protons is always a good thing to know acids because they're first. That's the first thing in line on a reaction that happens because it's so quick that there's no hesitation. It's always faster than everything else. So I think I'm running out of time on this video, but you have a great day, and always remember, science is great.